Hi there, I'm Kevin Slater. I'm an environmental scientist. I actually um, graduated a few years ago with a geology degree, and I work as an environmental scientist today. And I noticed that there's a distinct lack of um, climate change videos out there explaining all of the math and science behind it and why we know that it's being caused by humans. So I went out and I bought this at Walmart. I think that's up. And it's a whiteboard that I got some pens, got an eraser, and let's go over this. So any climate change discussion in classes, if you take climatology or meteorology classes, you'll start at the very beginning, and one of the best places to start is with electron energy levels. So perhaps you've seen this before, perhaps not. It looks kind of like this. Electron energy levels. This is the energy it takes to promote an electron. I believe the first one is 10.2-ish electron volts. That's the energy it takes to promote a hydrogen atom from base level up to the first level, and then up higher. This is how you take an electron and move it from like an S1 energy level to an S2 or a P3 or D2 or whatever. If you study electron configurations, they have certain configurations. This is the energy it takes to go from a base level up to a higher level. This is different for every single type of element, and of course also with every single type of chemical compound. It requires a very specific amount of energy to promote the electron to a higher energy level. After it promotes, it of course falls back down to the base level that it can get to, and then it gives off light. So if you have a source of light, so let's draw a little source of light here. If you have a source of light and you have an electron, and we'll just draw the most basic electron we can. Source of light, most basic type of electron we can, a hydrogen atom. When the light goes from the light source over to the hydrogen atom, only a very specific wavelength of light will cause that to promote, as I showed with the electron energy levels. It has to be exact. It promotes to a higher level, and then it falls back down to the base level. So when light is absorbed, we call it part of the absorption spectrum. When it's emitted, it is called the emission spectrum. And it emits light any path that it wants to in order to get back to the base level. So if I draw the electron energy levels again, and it looks kind of like that. When it goes up, it can go up to perhaps this energy level, and then when it falls down, it can go falling down there before falling down there. It can fall down here before falling down there before falling down there. It can fall all the way down to here before falling down, or it can just fall all the way down. It can take any path it wants to in order to get back to the base level, which means that the light that it emits is not exactly the light that is absorbed. And it can also emit that light in any direction it wants to. It can emit that light straight up, back this way, down. It can even send it back the same way it came in, but the chances of that are extremely small. And so when an atom or a molecule absorbs light, it is very unlikely for that light to continue on in the same direction and at the same intensity that it came in at. Of course, when you promote an electron like that, it causes heat. It excites the molecule. The molecule generates heat because it vibrates, and that heat is released into the system. It can be absorbed by other molecules in the area, blah, blah, blah. You can kind of understand that if you've taken any basic physics classes. This is actually quantized. Energy is quantized. This is where we get the word quantum mechanics from, because energy is quantized. It cannot absorb half of the energy it needs to promote. It can't absorb 3/4 of the energy. It must absorb all of the energy or nothing. Either the energy passes straight through because it's not absorbed, or it is all absorbed. It is quantized. This is basic quantum mechanics. Okay, so we know through study and through research, we know what every single element emits light at and what it absorbs light at. And we know most of the molecules, probably all of them, that we have, of course, here on Earth, and much of them in space. This is actually also how we tell what stars are made of. We can't actually travel to the sun and see what it's made of, but we can see the light that it gives off, and we can actually tell what it's made of by the emission spectrum of the sun. That's how it's done. That's how we know all of the stars. That's how we know the other planets, what they're made of. We don't have to go out there to Jupiter and see what it's made of. We can see what its emission spectrum is, its absorption spectrum from the sun, all of this stuff. So what this has to do with climate change is because the Earth, when it receives sunlight from the sun, draw the sun back, the Earth is somewhat reflective. About 30% of the light goes right back out into space because snow, ice, ground, plants, animals, all of that stuff, if it doesn't absorb the exact spectrum of incoming light, it's reflected back out into space. Some of that, of course, is absorbed by the ozone. So we'll put O3 here. Ozone, the ozone layer, absorbs a lot of the blue light from the sun, and then it heats up the Earth. The Earth has a different emission spectrum than the sun, and then it emits that back out. So we have what's called a black body radiation curve. So every single thing that you see, everything, me, the walls, the wall scrolls I have in the back, they give off energy when they're heated up. You know this when you have like a range on your stove and you heat it up. If you've got an electric stove, the range, the little thing that you have starts out black, and as you heat it up it becomes red, and if you keep heating it up it'll become white hot. It gives off different spectrums of light depending on how much heat it has, and if it were a perfect black body, it would be a black body radiation curve. Stars are pretty close to actual black bodies. They're not quite there, but they're almost there. And everything has a curve that it emits light at. And so the sun's emission curve looks like this. It peaks in green. In fact, I can use a green pen for that. It peaks in the green. That's the #1 light emission that the sun gives. Over here, the Earth peaks in the infrared. So you can't see this. This is infrared. Can't see this. This is what we call heat. Warm sidewalk on a warm sunny day, that's going to be giving off heat, which is infrared light. I wrote it up there on the top. So when the atmosphere of the Earth, we'll make this the atmosphere of the Earth, it lets in this light here in this range is almost entirely let through. Some of the blue light here at the end, of course, this is absorbed by the ozone. But most of this gets through, heats up the Earth, and is given off in this spectrum goes out and is absorbed by water vapor. Since it's water, we'll put it in here, water vapor. Absorbs the outgoing radiation from this. Also CO2, methane, nitric oxide. I think it's nitrous oxide, I don't remember. These are considered the greenhouse gases because it heats up the earth when it goes back out. Now we actually can calculate exactly how much that temperature is by the Stefan-Boltzmann equation, because Stefan-Boltzmann, they were a pair of scientists about a century ago that measured how much energy at different levels, how much heat would radiate at what temperatures, and they found a constant in the universe called the Stefan-Boltzmann constant. I won't write it down here. I've got a little cheat sheet though. And the temperature of everything, very simple equation, T equals, that's the temperature, the cube root of L over R squared theta 4 pi, right? And we know what all of these are. The amount of the temperature of something is the luminosity, and is there an R? That's an R. The reflectivity, you have the Stefan-Boltzmann constant, and then you can pop it through that formula and you get the exact temperature. And I'm not going to do all of it for you, but the temperature of the Earth is about 285 Kelvin. When you put it through that, because we know how reflective it is, about 30% reflective, we know how much the incoming radiation is from the sun, we know the surface area of the planet, and then we pop it through that equation, you get 285 degrees Kelvin. That's not accurate. That's not the temperature of the Earth. The reason why is we haven't taken into effect the greenhouse effect of the atmosphere, as the outgoing radiation adds about 30 degrees Kelvin. Okay? 30 degrees Kelvin brings it up to about 315 degrees Kelvin. If it was this, we would all freeze. The Earth would be a frozen ball of nothing. This is the temperature of the Earth. It's pretty constant. Doesn't change much over time, and it's due to the atmosphere that we have. So the atmosphere composition of the Earth, when we talk about the absorption rate of the different gases in the atmosphere, the number one is water vapor. That accounts for about 85% of the extra heat. So 85% of 30 degrees, it's about 26 degrees, 25 degrees, 26 degrees, close to 27 actually. Number two is CO2. That amounts for about 10%. 5% is methane. Number three, 5% is methane and everything else, and others. So this is how it goes. About 3% of the total 30 degrees Kelvin is caused by CO2. Okay, so if you took the CO2 on the Earth, which was about 285 before the Industrial Revolution, it's about 415 now. It's getting up there. Actually, I think it's, I don't remember. 415 is about right. It's getting bad. If you double this amount right here, you must increase the temperature of the Earth. It has to go up. It can't not. That is simple physics. It traps more energy. People talk about how it's already saturated, blah, blah, blah. We've already proven that wrong. People talk about how um, the energy from this extra heat that we trap because of the extra carbon dioxide in the atmosphere is actually negligible compared to water vapor. That's not true. 3 degrees, if you double that, 3 degrees. They talk about how the way the energy distribution is and the absorption rates, it's not going to affect it very much. That's also not true. All of these things have been worked out. We have worked these out time and time and time again. This is one of the most proven things in the field of geology. I mean, you'd have to deny that the Earth revolves around the sun. You would have to deny plate tectonics. That's the level of denial that you would have to make in order to pretend this doesn't exist. People have tried to argue, oh, it's water vapor that is to blame because we are evaporating too much water. Look at the Caspian Sea, or the Aral Sea, I think it is actually, the Aral Sea in Russia. We've evaporated that off. That's what's to cause. No. Water vapor, we have to discuss what's called brain freeze. Sorry. We have to talk about the length of time something stays in the atmosphere. The amount of time that water vapor spends in the atmosphere is about a week. A residence time. Thank you, me brain. Residence time. Okay, residence time is very important when we talk about anything in geology, when we talk about anything in atmospheric sciences. You have to talk about how long does something stay in the atmosphere. Water vapor is about a week. It can be about 10 days. So if you took the entire oceans of the Earth and evaporated them into the atmosphere, it would take about 1 week for all of it to rain back out and end up back down in the oceans. The Aral Sea, you evaporate the whole thing off, it's going to go somewhere. It'll evaporate, stay in the atmosphere, and then it'll rain back out, and it'll either go back to the ocean or it'll go into the rivers and groundwater. Whatever the case may be, evaporating more water is not going to cause climate change. It can't. 1 week is not enough time to cause climate change. CO2, of course, stays in the atmosphere for about 100 years. And so the more CO2 you put in the atmosphere, it's going to stay there. And it's going to cause warming. And the more water vapor, the warmer it is, the more water vapor can be absorbed in the atmosphere. That's easily provable. You go outside on a cold winter day, there's going to be very little humidity. The air feels crisp. The reason why it feels crisp because there is very little water vapor in it. Warm water holds more water vapor. If you go down to the jungles of South America, it's going to be very muggy. It's going to be very humid. Southwestern United States is very dry. Southeastern United States is very humid. So if you have been to either of those places, you know what humidity is like. And the hotter it is, the more water vapor the atmosphere can hold, not necessarily will hold, because it depends on weather patterns. But that's why water vapor is not a driver of climate change, but CO2 is. Some of the more things that we can talk about. We can talk about C13 in the atmosphere. C12, of course, that's the common carbon-12. That's the common isotope of carbon. C13 is less than 1%, but it's about a 0.5%. We'll just put a 0.5% to make it easy. It's not, but just to make it easy, we'll say it's a 0.5%. So plants, it's called carbon fractionation. Carbon fractionation is very important. So plants prefer C12, which is lighter and easier to use than C13. It's not like they're consciously thinking of this. They don't really have brains. But when they are capturing carbon from the atmosphere to make into all of their leaves and stems and all of that stuff, it is much easier to capture carbon-12 because it's lighter than it is to capture carbon-13. So they were going to capture more of it out of the atmosphere than carbon-13. So plants, and that's carbon fractionation, plants have less C13 than the atmosphere. Okay, very easy. Plants have less C13 than the atmosphere. They also have less C14. C14 is not a very good indicator because unfortunately all the atom bombs we blew up in the 1960s released a lot of carbon-14 in the atmosphere. So we don't use it. We use C13 instead. Carbon fractionation. Plants have less C13 than the atmosphere, and less C14 as well. That comes up a little bit. So if you have a source of carbon in the atmosphere and you're wondering where it's coming from, it is very easy. Volcanoes don't care. Okay? Seabed. Carbon doesn't care. Okay, so if the source is like hurricanes blowing through, picking up and churning material off the seabed, and it's releasing carbon dioxide into the atmosphere, some people have argued that that's where our carbon's coming from in the atmosphere. It doesn't care about carbon fractionation. Seabed doesn't fractionate carbon. Volcanoes doesn't fractionate carbon. Plants do. So if you have relatively the same amount of carbon-13 in the atmosphere over time, then the source would be volcanoes or the seabed. If, however, carbon-13 is falling in the atmosphere while overall carbon is going up, then the source is plants. Very simple. And what do we see? We see carbon going up, overall carbon, while C13 is going down, right? That's what we see when we go out and we look for what's going on in the atmosphere. The source is not volcanoes. The source is not the seabed. The source is not any other source but plants. It's coming from plants. And we know that the primary source of coal and oil on the earth is caused by plants. We know this, right? And the C13 is dropping. The source is plants. We know coal and oil are made of plants. The source isn't volcanoes. It isn't seabed. It's coal and oil. Okay? There's no other good source. You can burn trees and also release that. And by the way, we are burning trees. That's not good either. It also contributes to climate change. We know this. All of these things are man-made. Okay? Carbon fractionation proves all the deniers wrong. We know the source of the carbon in the atmosphere. We know what carbon will do when you increase it in the atmosphere. It must cause heating. The end. There's no more arguments. That's it. Good day.